Now theorem 3. This is basically the inverse of theorem 1, which states that parallelogram on the same base and between same parallels are equal in area. The theorem 3 states that parallelograms on the same base and having equal areas lie between the same parallels. Now let's prove this. It is given that ABCD and EFCD are parallelograms. It is also given that area of ABCD is equal to area of EFCD. And we need to prove that AB and EF lie on the same parallel. For this, let us construct two perpendiculars from A and E to CD. So now, area of ABCD is equal to base CD and height AX. Also, area of parallelogram EFCD is equal to base CD and height EY. Therefore, I can say that AX is equals to EY. That is, AX is equals to EY. And these two can only be equal when AB and EF lie on the same parallels. Now the next theorem. The theorem states that parallelograms on the equal base and between same parallels are equal in area. Now this theorem is somewhat similar to theorem 1. In theorem 1, it was given that parallelograms on the same base and between the same parallels are equal in area. But the theorem 4 states that parallelograms on the equal base and between same parallels are equal in area. So we have these two parallelograms where base CD and GH are equal. So it is given that ABCD and EFGH are parallelograms. It is also given that CD is equals to GH. That is, base of both the parallelograms are equal. So we need to prove that, area of ABCD is equal to area of EFGH. We know that area of parallelogram is the product of base and height. Therefore, area of parallelogram ABCD is CD into the height of the parallelogram. Let it be H1. Also, area of parallelogram EFGH is equals to GH into height. Let it be H2. Now, since these two parallelograms lie between the same parallel, so I can say that H1 is equals to H2. So H1 is the distance between AB and CD and H2 is the distance between EF and GH. And since these two lie between the same parallel, therefore the distance between same parallel lines should be equal. Therefore H1 is equals to H2. Now since H1 is equals to H2 and CD is equals to GH, therefore I can say that the area of parallelogram ABCD should be equal to the area of parallelogram EFGH. Therefore, I can say that parallelograms on the equal base and between the same parallels are equal in area. If we study the theorem 1 and 4 carefully, we can say that parallelograms on the same or equal base and between the same parallels are equal in area. Now theorem 5. Theorem 5 is again an inverse of theorem 4. It states that parallelograms on the equal base and having equal areas lie between the same parallels. Now let us prove this theorem. We know that area of parallelogram is base into height, and here the areas of parallelogram are equal. Let the base and height of parallelogram 1 be B1 and H1 and parallelogram 2b, b2 and h2. It is also given that the bases are equal. Therefore, b1 is equals to b2. It is also given that the areas are equal. Therefore, b1h1 is equals to b2h2. Let's write b1 and b2 as b. So b and b will cancel out and we'll get h1 is equals to h2. That is, height of both the parallelograms should be equal, and this can only be possible if they lie between the same parallels. Therefore, on rewriting the above theorem, we get parallelograms on the same or equal base and having equal areas lie between the same parallels. Therefore, the addition here is the bases are equal.